right, so we are looking at section 3.2, page 229, logarithmic functions. For some reason, logarithms strike fear in the hearts of math students everywhere. They are really not that bad. You saw them in Algebra 2, so seeing them the second time, hopefully this will make a lot more sense to you and seem a lot easier to you than perhaps it did the first time around. All right, so when we are talking about the definition of a logarithmic function, they tell me that if I have a logarithmic function with a base of a has to be a number greater than 0 and not equal to 1. Now, that ought to sound familiar because we saw that exact same restriction, a is greater than 0 and a is not equal to 1, somewhere before. Where did we see that? With the exponential functions, right. And so the reason that we have the exact same restriction on the base of our logarithm as we did with the base of our exponential is because exponentials and logarithmics are inverses of each other. They're going to undo each other. We're actually going to be able to switch from logarithmic form to exponential form and vice versa. And so the restrictions on a are going to have to remain the same whether it's the base of our logarithm or whether it's the base of our exponential. The only other restriction is that x has to be a number greater than 0. So what you're taking the log of, no matter what your base is, what you're taking the log of is going to have to be greater than 0. So grab your graphing calculator, if you would, for just a second. Graphing or scientific, it doesn't really matter. And on your calculator, let's put in the log of a negative number. So you've got a log button right over here in the first column. So let's put in the log of a negative number. It doesn't matter. Pick any negative number that you want to. If you ask your calculator to evaluate the log of a negative number, it's going to tell you error. That's not a real answer. Or it might even say error domain sometimes. The same thing is true if I ask it to take the log of 0. So if I went back and I asked it to evaluate the log of 0, same thing is going to happen. It's going to tell me error domain. And what it's specifying for me there is that the domain of a logarithmic function, the only values that I can put in for x are values greater than 0. You cannot take the log of 0. You cannot take the log of a negative number. It's not possible. Okay? So, for our logarithmic function, if we have something that is f of x is equal to the log of x with a base of a, we could switch that from its logarithmic form to its exponential form by following this pattern or this definition. Whatever the base of your log is going to be the base of your exponential. The answer to your log will be your exponent on your exponential, and what you were taking the log of will be the answer on your exponential. I think it's easier to see with numbers, so let's put some numbers in there. Let's say that we had the log base 2 of 8 is equal to 3. If we wanted to switch that to an exponential, then we would say, okay, my base was 2, and again, following my pattern, a was 2, so I come over here, a is 2. Then the next thing I need is y for my exponent, so I can come over here and say, okay, y was 3, so my exponent will be 3. And then my answer needs to be x, so I can come over here and say x was 8, so I can give my answer of 8. So as long as I follow that pattern or that rule, then I can switch from my logarithmic form to my exponential form. And I could also go the opposite way. I could go from the exponential form back to the logarithmic form. All right, so for the first example, they asked me to change from logarithmic form to exponential form exactly as we were just doing. So on your paper, go ahead and use that pattern to switch the log base 3 of 81 equals 4 over to an exponential function. Follow that same pattern, whether you like the letter version of it or the number version of it. So what'd you get when you switched it over? Perfect. 3 to the 4th is equal to 81. Now, this doesn't happen very often on our exercises, but you'll notice these little numbers right here in red. Those are the homework problems that are going to correspond to the example that we're working with, and we have examples for almost everything we're going to see on the homework tonight. The reason for that is we're going to have several days to work with these logarithmic functions, and yes, we will get to higher thinking skills and applications where they're not going to give me an example. I'm going to need to apply the skills myself and do some synthesis and figure it out on my own. But at this stage where we're just reviewing the basics and trying to get that back in our mind, then yeah, we're going to have an example that's just like each of the things that we're going to see. So that'll be really helpful for us tonight. All right, so for numbers 9 through 18, they're going to ask me to go the opposite way. Here's your exponential function. Let's switch it to a logarithmic. So again, I just want to match these up. I want to say log base A. What was A over here? 4. So we'll have log base 4 of x. What was x? X was 16 is equal to y. What was y? Perfect. So we'll have the log base 4 of 16 is equal to 2. And you can spot check it. 4 to the second equals 16. Yeah, that works. All right. Then in example number 1, and for problems 19 through 24, they're going to ask us to simplify or evaluate the logarithms. So they're going to say, what's the log base 2 of 32 equal to? So I usually just come over here and put a little x in the blank so that I can switch it over to its exponential form. So if I take this logarithmic form and switch it to exponential form, what am I going to have? 2 to the x is equal to 32. So the best way to attack your logarithms is to switch them over to their exponential forms. You're comfortable with exponentials. You know how to evaluate those. So switch your logarithms to exponentials and then go from there. Now, there are going to be some of these that you can just look at and automatically know the answer. A lot of you, when you're looking at this, you already know what the answer is. But we may get to some a little later on where you look at it and you don't instantly know what the answer is. And so we're going to evaluate all of these the same way so that when we get to ones that maybe we don't know, we still have a method of evaluation. So once I get it into this form, anytime I have an unknown in my exponent, the way that we solve that algebraically is we try to get our bases the same so we can set our exponents equal to each other. So I'm going to try and rewrite 2 and 32 with a common base. So what base could I use? 2. So we could rewrite 32 as 2 to the what? 5th, right. So if we rewrite 32 as 2 to the 5th, now my bases are the same, so I can set my exponents equal to each other, so I know that x is equal to 5. All right, look at the next one. What's my exponential form? 3 to the x is equal to 27. My unknown is in my exponent, so I want to try and get my bases the same. So I'm going to rewrite 3 and 27 with a common base of what? 3. So 27 would be 3 to the what? 3rd. So now my bases are the same. I can set my exponents equal to each other, and I know that x is equal to 3. All right, how about the next one? What's this in exponential form? 4 to the x is equal to 2. So this might be the first one that you come to that's not immediately obvious to you, where you look at that and you're like, okay, 4 to the 1 is 4. That's too big. Okay, 4 to the 0 is 1. That's too small. Not sure what's going on there. So again, let's try and get this where my bases are the same. So I'm going to rewrite 2 and 4 with a common base of 2. So I'm going to rewrite 4 as 2 squared. So I'm going to replace 4 with what it's equal to, 2 squared. So now I have 2 squared to the x. When you have a power raised to a power, what do? Multiply, right. So I'm going to multiply that 2 times x. We had 2 squared to the x. That was a power raised to a power. So we multiplied 2 times x and got 2x. Now my bases are the same, so I can set my exponents equal to each other. So I'm going to set 2x equal to 1. So what's x equal to? 1/2. And it makes sense after we see it, because if you raise something to the 1/2, that's the same thing as doing what? Square root. So yeah, square root of 4 is 2. But I might not have thought of that instantly when I saw the problem. All right, what's the exponential form for this one? Yeah, 10 to the x is equal to 1 over 100. So again, I need a common base for 10 and 1 over 100. All right, so what common base can I use? All right, I heard 1 over 100 and I heard 10. I probably could go both ways with this. Most of us, I think, would prefer a whole number to a fraction, so I'm going to go with the 10. All right, so if this guy is already written with a base of 10, so what is 100 with a base of 10? 10 squared, right. So if I rewrite 100 as 10 squared, then I need to get it up to the top. So how do I move it up to the top? Negative 2, right, negative exponent. So now my bases are the same, and I can set my exponents equal to each other, so that means that x equals negative 2. And if I go back and look at it, it makes sense. If this was 10 to the negative 2, that would be 1 over 10 to the positive 2, or 1 over 100. So yeah. All right, look at the next one. What is this in exponential form? 3 to the x is equal to 1. And there's not an algebraic way of doing this. It really just requires that I remember a rule about exponents. And that is, other than 0, which we don't have to contend with in our values that we're working with, but other than 0, any value to what gives me 1? 0, right. Anything to the 0, other than 0, which we don't deal with here, is equal to 1. So that rule is what I need to remember when I see this. That's the only way that I'm going to come up with that answer of x is equal to 0. But to try to help me remember that, they're going to give me some properties of logarithms that are basically like shortcuts for logarithms, things that would always be true that might help us. And the very first one they give me is that the log of 1 is always going to be 0. And we can see why that would be true if we switch it from its logarithmic to its exponential form. You're going to have your base to the 0, which again is always going to be 1 unless a is 0, and a can't be 0 when we're working with exponentials and logarithmics. All right, so the next one, we've got log base 2 of 2 is equal to x. So what's that in exponential form? Yeah, 2 to the x is equal to 2. What's my exponent here? 1. So my bases are already the same. I can set my exponents equal to each other, and I'll get x equals 1. And we actually just discovered the second property of logarithms that they give us, and that is if you're taking the log of something and you have the same base, that answer is going to be 1. And you can see why if you switched it over to its exponential form, you're basically getting an identity over there. So when we were taking the log of 2 and we had that same base, we got an answer of 1. So let's look at a couple more properties. If exponentials and logarithmics are inverses of each other, which they are, then remember we learned about inverses that if you do a composition of those functions, they undo each other and just take you back to what you started with. They take you back to x. And so that's what we see for our next two properties here. If you take the log of an exponential, their bases have to be the same. They will undo each other and just leave you with x. And that makes sense because if you switch it from its logarithmic form to its exponential form, you just have an identity. The opposite is also true if you take the exponential and you raise it to a logarithmic. As long as the bases are the same, they'll undo each other and they'll take you back to where you started from, which is just x. And again, if you switch that from its logarithmic form over, from its exponential form over to its logarithmic form, again, you just get an identity, so you can see why that statement would be true. All right, the last one they tell me is that if you are told that two logs are equal to each other and their bases are the same, then what you were taking the log of would also have to be the same. So if they give me something like the log base 2 of x is equal to the log base 2 of 3, what does x have to equal? 3, right. So that's just an example of that last property. All right, we joke all the time about mathematicians being the laziest people on the face of the earth. We take shortcuts everywhere we can. Here's another one of those. You know how when we're working with radicals, if there's no number written on the radical, we assume it to be what kind of a root? Square root. And we do that because that's the one that we use most often, right? So we get too lazy. We don't want to write the 2 every time. So if there's no number there, we assume it's a 2. We do the same thing with logarithms. The most common logarithm that we work with is a log base 10. And so the log base 10 is known as the common logarithm. And if you see a log that does not have a base, you can assume that it's a base of 10. The log button that's on your calculator, it doesn't have a base, right? That's a log base 10 button. That's your common log button. So when they ask you to find the log of 3, literally that's the log base 10 of 3. So throw that into